In the previous lesson, we learned that stability depends on where the poles of the transfer function are located. All poles must be in the left half-plane for BIBO stability. But finding the exact roots of a polynomial can be difficult, especially for higher-order systems. Is there a way to check stability without actually computing the roots? The answer is yes. The Routh-Hurwitz criterion gives us an algebraic test. We only need the coefficients of the characteristic polynomial. Every LTI system described by a transfer function has a characteristic polynomial. It is the denominator of the transfer function. We write it as a n times s to the n plus a n minus 1 times s to the n minus 1 all the way down to a 1 times s plus a 0. The roots of this polynomial are the poles. The Routh-Hurwitz criterion tells us how many of these roots lie in the right half-plane without solving for them. Before building the Routh table, there are two quick necessary conditions for stability. First, all coefficients must be present. If any coefficient is 0, the system cannot be stable. Second, all coefficients must have the same sign. If any coefficient differs in sign from the others, there is at least one root in the right half-plane. These conditions are necessary but not sufficient. Even if both are satisfied, we still need the Routh table to confirm stability. Now let us build the Routh table. The table has n plus 1 rows, where n is the degree of the polynomial. The first two rows come directly from the coefficients. Row s to the n gets the odd indexed coefficients, an minus 2, an minus 4, and so on. Row s to the n minus 1 gets the even indexed coefficients, an minus 1, an minus 3, an minus 5, and so on. Each row is labeled by descending powers of s. The remaining rows are computed using a cross-multiplication formula. For each entry, we take the element above and to the left, multiply it by the element diagonally above and to the right. Then subtract the reverse diagonal product and divide by the element above and to the left. This pattern repeats row by row until we reach the s to the 0 row. Each row has one fewer element than the previous row, until the last row has a single entry. The Routh-Hurwitz criterion states, the number of sign changes in the first column of the Routh table equals the number of roots in the right half-plane. If there are 0 sign changes, all roots are in the left half-plane and the system is stable. If there is one sign change, there is one unstable root. 2 sign changes mean 2 unstable roots, and so on. We only need to look at the first column. Let us work through a third-order example. Consider the characteristic polynomial s cubed plus 6s squared plus 11s plus 6. First, check the necessary conditions. All coefficients are present and positive. Good. Now build the Routh table. Row s cubed gets 1 and 11. Row s squared gets 6 and 6. For the s to the 1 row, 6 times 11 minus 1 times 6, all divided by 6. That gives 60 minus 6 over 6, which is 9. For the s to the 0 row, 9 times 6 minus 6 times 0 divided by 9, which gives 6. The first column is 1, 6, 9, 6. No sign changes. The system is stable. Two special cases can arise. First, a 0 in the first column, but the rest of the row is not all zeros. In this case, replace the 0 with a small positive number epsilon. Continue the table, and then examine the sign changes as epsilon approaches 0. Second, an entire row of zeros. This indicates that the polynomial has symmetric roots about the origin. We form an auxiliary polynomial from the row above, take its derivative, and use the derivative coefficients to replace the 0 row. Then continue as normal. Let us summarize. The Routh-Hurwitz criterion checks stability using only the polynomial coefficients. Step 1. Verify that all coefficients are present and have the same sign. Step 2. Build the Routh table from the coefficients. Step 3. Count the sign changes in the first column. 0 sign changes means all poles are in the left half plane. The system is stable. In the next lesson, we will study time domain specifications, rise time, settling time, overshoot, and how they relate to pole locations.